Okay, so this module is called Spectral Analysis, and so what we'll be primarily dealing with it is eigenvalues and eigenvectors, and you'll also use them in the later modules too. So it's very important to get a good understanding of eigenvalues and eigenvectors. Okay? Uh, well, I'll explain the basic things in this module. Even though you might have seen this in a math course before, it doesn't really require you to come across this already. I have explained it, the basic things that you really need to know for this course. Okay, so let us do this. Alright, so before we really do what is called the spectral analysis, let me just introduce what eigenvalue and eigenvector mean. Okay, consider say a square matrix, n by n matrix. Now something like 3 2 3 negative 2, this is n by n 2 by 2 square matrix. Now let us call that matrix as A. Now for this square matrix, if we can come up with what is called a scalar value, scalar means some number, it could be an integer or it could be a real number, some value, some single value, scalar. Okay, and what is called column vector you can also call just a vector. Okay, like this is a vector. The number of entries in the vector will be same as the dimension of your matrix. So if you can come up with a scalar and the corresponding vector such that the matrix times that vector x equals that scalar value times that x, then the scalar value is called the eigenvalue and the corresponding vector is called the eigenvector of that matrix. So let's go through this example. So you have this matrix here, A is 3 2 and 3 negative 2. Now I already have found out eigenvalue and eigenvector for this matrix, and in this module we'll see how to do that as using some applications. But right now assume that this is an eigenvalue and this is a corresponding eigenvector for this matrix. So we're going to check whether this property is satisfied. So according to this property, the matrix multiplied by its eigenvector, which is 2 1, so I'm going to multiply this matrix with this vector 2 1, should be equal to the scalar value 4 times the vector 2 1. Let us check on each side. So here I have a 2 by 2 matrix multiplied by 2 rows 1 column matrix. So it's going to be like what? 2 by 2 matrix multiplied by 2 rows 1 column. So the product is going to be 2 rows 1 column. So 2 rows 1 column is just like you have one entry and another entry. So this is what you're going to find out. Okay, so to find out say row 1 column 1, we have to basically multiply row 1 column 1. So it is 3 times this 2 plus 2 times this 1, that's going to be 8. Then to get this entry, which is row 2 column 1, you have to multiply row 2 column 1, which is 3 times 2 plus negative 2 times 1, that is 4. Okay, so this is 6 plus 2 8, then 6 minus 2 4. Now that's on the left hand side. On the right hand side we have 4 times 2 and 4 times 1, so it's also 8 4. So both left hand side, right hand side are the same. So we say that this property is satisfied. So what is the property? The matrix multiplied by its eigenvector should be equal to the scalar value multiplied by its eigenvector. So then you can say the scalar value 4 in this case is the eigenvalue, and the corresponding matrix, the vector, is called the eigenvector. Okay. Now for a given matrix, how many such eigenvalues and eigenvectors you can have? So it depends on the dimension of the matrix. So this is a 2 by 2 matrix. It's a square matrix, right? So it's a 2 by 2 matrix, and so you're going to have 2 eigenvalues, and for each eigenvalue will have a corresponding eigenvector. So the eigenvalue and eigenvector are related to each other, okay, because you should be able to satisfy this property. Okay, so if you just pick some random value as eigenvalue, you need to have a corresponding eigenvector. So for every integer or every decimal number out there, we cannot have a corresponding eigenvector that satisfies this property. So they should be mathematically related, eigenvalues and eigenvectors. Okay. So in general, for an n by n matrix, you're going to have n eigenvalues, and for each of those eigenvalues, you'll have a corresponding eigenvector. Okay. So with that background, so any question on this, eigenvalues, eigenvectors? Okay, that's fine. Alright, so let us move on. Okay, so by spectral analysis, or it's also called spectral decomposition, what I mean is, or the kind of definition is, projecting the characteristics of a network graph in n dimensions or directions, where the directions or dimensions are mutually perpendicular to each other, and n is the number of vertices in the graph. So basically, we have a graph, and they're trying to find out or kind of project this graph in n dimensions and try to find out which dimension is more significant. Okay, and all the dimensions are going to be perpendicular to each other, right? Now the projection in each direction is called the eigenvalue, and the associated vector with an eigenvalue is called the eigenvector. The largest eigenvalue of the projection is called the principal eigenvalue, and is also called the spectral radius, and the corresponding eigenvector is called the principal eigenvector. Okay, and we'll see all these things using this example. I'm just going over the definitions, and I'll come back to this slide and go over those definitions again. And then so we will use the adjacency matrix. As you saw in this example, we need a matrix to compute the eigenvalues and eigenvectors. So we will use the adjacency matrix of a graph as our matrix to compute the eigenvalues and eigenvectors of that graph. Okay, so let us take this example. So this is a matrix. So we will talk about the, okay, let me tell right away. So there is a method called well, that will give you only, okay, there are some methods available in the literature to compute the eigenvalues and eigenvectors of a graph. Okay, but we're not going to go through the math behind those methods. Okay, it's a very time consuming process, of course. So to compute the eigenvalues and eigenvectors even for a 10 by 10 matrix, because this is a 10 vertex graph, so you're going to have an adjacency matrix with 10 rows and 10 columns. So it's going to take a lot of time. So what I have done is I have used the packages available in the programming languages. So I use Java as a programming language that comes up with some built-in packages to compute the eigenvalues and eigenvectors of the matrices. So I have used those packages, and I've written code to use those packages and compute the eigenvalues and eigenvectors. And I'm going to share that code with you people, and you can use that code to run for any graph and get some results and do the analysis like what we're going to do in this module and the rest of the other modules too. Okay. So those programs I'm going to share with you will require an input which could be the adjacency list of the graph or adjacency matrix. So I'm going to share both the versions. The adjacency list may be more easier to type and run it, because adjacency matrix you have to have square matrix and fill it up with zeros and ones carefully and so on. If you do any small mistake, results will be different. So that's why I suggest an adjacency list based approach. But for some kind of topics, you need to have use an adjacency matrix. For some topics, in that case, I'll mention that. Otherwise, you could use adjacency list as much as possible. Okay. So to get the eigenvalues and eigenvectors for a graph, you could use an adjacency list or an adjacency matrix. So okay, so this is the convention we will follow to get a adjacency list. You could type them in any order, and the program I have written is good enough in such a way it will still be able to print the eigenvalues irrespective of in what order you type the adjacency list. But let us, for uniformity, will follow this convention. So we'll again, I think I mentioned this before in the first module too. So you'll have the lower, for any edge, the lower ID vertex as the left side or as the first end vertex, and the higher ID vertex as the other end vertex. So, and again we'll start with the lower ID vertex. So we'll look at the neighbors of 1. So it's going to be for 1, 1, 2, 1, 3, 1, 4 and 1, 5. So done with 1, then we'll go to 2. So for 2 we'll have 2, 3. You don't need to write 2, 1 again, because 2, 1, this is undirected graph. So 2, 1 is same as 1, 2. So it's already captured in 1, 2. So don't need to write 2, 1 again. So you can say 2, 3, 2, 4 and 2, 6 are the edges associated with 2. Then for 3, there's no need to write 3, 1 or 3, 2. Just write 3, 4 and 3, 8. So basically a vertex and its higher ID neighbor. Then for 4, all its neighbors are lower ID neighbors. So you don't need to write 4, any edge for 4, because all those edges associated with 4 are already captured. Then 5, I don't need to write 5, 1, because 1 is a lower ID neighbor already captured here. So write 5, 6, 5, 7, 5, 9 and 5, 10. And then for 6, the neighbors are like lower ID already captured earlier. So then 7, you need to write just 7, 8, not 7, 5. Then 8, there's no need to write anything for 8. Then 9, again lower ID neighbor. 10, you have this lower ID neighbor. So these are all the edges in this graph. Again, you can cross check whether you have missed any edge. Okay, just go through all the edges and you can count the edges if you want to, and make sure you have the count here is same as the count on this graph. Right, so if you follow the way I explained now, it's going to be easy for you. So basically, let me repeat again. So start with the lower ID vertex and write all its higher ID neighbors. So start with 1, write all the higher ID neighbors 2, 3, 2, 4, and so 1, 2, 1, 3, 1, 4, and then for 2 you have 2, 3, 2, 4, and then 2, 6. Then for 3, write 3, 4, and 3, 8. So the other second vertex to be higher ID. Then 4, you don't have any higher ID neighbors, so just leave 4. Then 5, you have 6, 7, 9 and 10. 7, you have only 8. Okay. So once you type it up, you pass this as input to the program. So I have posted what is called a jar file in the since we are open there, so I can go there. So in the modules section, for this I have separately posted the jar files. So you can download these jar files. These are zip files, and extract all the files inside. So after you extract the files, for the adjacency list case, it will be like this. So it will be a folder. Okay. So I have posted this jar files. So once you unzip these files, you will see all these files. So that's just so it's already there's a folder. So you don't need to create a separate folder. So copy the folder separately to anywhere in your computer. Now one requirement is you just need to have Java installed in your computer. Okay, so make sure you have installed Java in your computer. Of course, you're all graduate students, so you should be able to install it if you don't have it already. Even if you have a Mac machine, just install the Mac version of Java, it should be fine. So I have put together all the files you need. So these are some examples which you may not want. So these are the critical things that you need: the manifest file, the JAMA file, and the class files, and the executable jar file. Okay, so everything you have, you don't have to check anything. I just mention this to you. So this is the so you always double click the executable file, not the JAMA file, but the EVC underscore adjacency list. So you're going to have only one such executable file in your code other than the JAMA file. So double click on the EVC underscore adjacency list to run the executable, and that will ask you to load the adjacency list. So I'm going to type the adjacency list first, so don't worry about what we just got. So I'm going to type the adjacency list, or you can copy and paste this. Now you could leave as you type, how you type the adjacency list. Some people may have a question. So you could just have a blank space in between the node IDs. You could have just a blank space like that, or you could have a tab and put 1, 2. So either way is fine. So 1 tab 3 2, or 1 tab 3, and then, or just like 1 space 4. Either way should be fine. Okay. So here I'm just going to copy this thing. Now one thing you have to make sure, otherwise my program will crash. So make sure there's no blank line. So right now there's a blank line after the 7 8. So there should not be any blank line. So the way you make sure that is, take your cursor back to the end of that last line 8 here, and make sure you press the delete button a couple of times, so that you don't have a next line created there. So if you press the down arrow now at 8 on that last line, the cursor should not move further down. So it should be there. That's where the cursor should be, the last line. So make sure your text file doesn't have any blank line as the last line. Okay, so this is the last line. So once you make sure that, save this to some name, whatever name you want. So let me say it as graph1 dot, and it could be stored anywhere at any folder. Okay, wherever you want to store it, that's fine. So again, as a requirement, make sure the text file doesn't have a blank line as the last line. This should be the last line where you have the last edge information. So now what you do is double click on this executable file and load that text file that you just saved. So I saved it. So wherever you save it, make sure you remember that. So go to that folder wherever you saved it and load that text file. And so I saved it under name graph -1. So this is the file. So it's going to compute the eigenvalues and the eigenvectors corresponding to each of those eigenvalues. So the eigenvalues are numbered 0 through 9 because I'm just printing the contents from an array. So that's the index 0 through 9. And for each eigenvalue, you have an eigenvector, as you can see. And the entries in the eigenvector really correspond to the vertices that you have in the graph. So this graph has vertices ID 1 through 10. So the entries that you have in the eigenvector really correspond to that. Okay. So now you see there are going to be 10 eigenvalues for this graph, right? So I have shown that here. So let us go back to this. So these are the 10 eigenvalues in the top row: 3.3893, 1.888, 1.1131, 0.31970, then negative. So the first row basically in this figure representation is your eigenvalues. So these are the 10 eigenvalues because it's a 10 vertex graph. You're going to have 10 eigenvalues, and that's what is output by this program. It's going to print all those eigenvalues. Now it's printing the eigenvalues from smaller to largest. Either anything is fine, but the numbers are the same. So I have 3.3893 followed by 1.8888 followed by 1.113, 0.31970. So it's printing from largest to smallest. So smallest to largest. But we typically use only the largest eigenvalue and the eigenvector associated with it. So if you go back to the definition, the largest eigenvalue is called the principal eigenvalue. It's also called the spectral radius of the graph. So for this given graph, the largest eigenvalue is 3.3893. So that's called the principal eigenvalue. Okay, and it's also called the spectral radius of the graph. Okay, and the eigenvector corresponding to the principal eigenvalue is called the principal eigenvector of that graph. Okay, so for each of these eigenvalues I have printed here. So eigenvector for index 9 with eigenvalue 3.3893 is this. Then eigenvector for index 8 with eigenvalue 1.888 is this eigenvector, and so on. Okay, so for each eigenvalue, my output program will output the corresponding eigenvector. So you can save this result to a file if you want to look at it anytime, because if you run your you may have to use the results several times in your calculations. So if you happen to shut down your computer and stuff like that, you don't have to run this program every time. Of course, it will not take much time. You can run it quickly and get the results again. But if you want to save the results to a text file, that is fine. So just click save to a file, and that will save the results to a text file, and you can open the text file and analyze the results, look at the numbers. Okay, so of course it's not really formatted that well. Okay, but the output looks very formatted, so that's why I prefer to work with the output itself. Alright, so these values are shown here in the slide here, so we will use these numbers. I have just used the first 4 decimals. As you can see, they can run up to very large number of decimal positions. The first 4 decimals are typically what we make use of. Okay. Alright, so any questions so far? Okay, so it's very important to understand how to use all this stuff. So let me continue. Alright, so you have the eigenvalues and the corresponding eigenvectors. So this is called the principal eigenvector because it is an eigenvector corresponding to the largest eigenvalue. And as I said, the entries correspond to the entries you have also represent something about the vertices. So it's node IDs and then the vectors, right? Alright, so later in module 3 we'll look at something called centrality metrics. So like eccentricity that we saw in the earlier module, eccentricity for a particular vertex, you can also have a centrality value for a particular vertex. And there is one type, so there are several centrality metrics we'll come across, and one centrality metric is eigenvector centrality. So the entries in the principal eigenvector basically capture the eigenvector centrality of the vertices. And eigenvector centrality, for now, you can think about it as it's a measure of the degree of the node as well as the degree of its neighbors. So a degree, you all know what it is. So degree means the number of neighbors for a node, right? That's what's called the degree of a node, and it's also called degree centrality. So the eigenvector centrality is a measure of how the degree of a node as well as the degree of its neighbors, and it captures all these things and represents one single number. So the larger the eigenvector centrality for a vertex, okay, the more important is a vertex from the eigenvector. That means it has more degree as well as its neighbors have a larger degree. Is that clear? So let us look at these numbers again. So the vertex that has the largest of the eigenvector centrality in this entry is vertex 1. It has 0.4741. So that means this vertex 1 has a larger degree, and it's reasonable, it has a degree of 4, and its neighbors, which are like what, 2, 3, 4 and 5, also have a larger degree. So 2 has a degree 4, 3 has a degree 4, 4 has degree 3, 5 has degree 5. So the vertex that has a larger degree and its neighbors also have a larger degree is more likely to have a higher value for the eigenvector centrality. On the other hand, look at vertex 5. It has an eigenvector centrality of 0.2986, and you can see it has a larger degree. It has actually the largest of the degree of all the vertices. It has a degree of 5. No other vertex has a degree of 5. But its neighbors don't have a larger degree that much. Its neighbors are like what, 9, 10, they have a degree of 1, 6 and 7 have a degree of 2, it's just 1 has a degree of 4. So it's not sufficient for a vertex to have a larger degree. Its neighbors should also have a larger degree. So in that way, 5 is going to have a lower eigenvector centrality of 0.2986 compared to vertex 1. Okay. So this is a good comparison to understand eigenvector centrality, what it indicates really. Okay. Now you can also think about, say, let us look at 6 and 8, for example. 6 and 8 both have a degree of 2, right? 6 has degree 2, 8 also has degree 2. But you see 6 is connected to 5 and 2. Both have reasonably larger degree. 2 has degree 4, 5 has degree 5. Whereas 8 is connected to 3 and 7. 3 has degree 4, but 7 has only degree 2. So if you look at the eigenvector centrality for 6 and 8, 6 has 0.2229, whereas 8 has 0.1724. So 6 has a larger eigenvector centrality compared to 8. Okay. So again, it depends on the degree of the vertex as well as the degree of its neighbors. In this case, 7 has a lower degree compared to 5, so that's why 6 has a larger eigenvector centrality. So in again module 3, you will see one method called the power iteration method to compute only the principal eigenvector and the principal eigenvalue. So as I said, there are other methods also available in the math literature to compute all the eigenvalues and all the eigenvectors, but we are not going to really need all the eigenvectors for our calculations. We may need for some approaches the smallest eigenvector and maybe all the eigenvectors for some applications, but we have this package to give us, this program is available now to compute all the eigenvectors for us, so we don't need to spend time going through the math to compute all these things. But we'll see one method and the math behind it to compute just this entry, the principal eigenvector, which is called the eigenvector centrality of the vertices, and the eigenvalue. It will be important to know one method to do the calculations. We'll see that in module 3. So right now for this module, we use this program, the jar files, to compute the eigenvalues and eigenvectors. Now one interesting property you can notice is if the matrix has all positive entries. By matrix here I mean the adjacency matrix that is behind this graph, because for this graph you can also come up with the adjacency matrix and compute the same eigenvalues and eigenvectors. So I have given you the jar files for both. So how you come up with the adjacency matrix, the convention, let me show you that, even though you may not need it. Let us show that. I think I may have an example here. Okay, I don't have an example, but let me see. I may have it some other course. Okay. Alright, let me just, I saw this just to make sure the convention is there. So this is how you type the adjacency matrix. So it's little not formatted, but this should be reasonably good. So you type all the node IDs 1 to 10 and as rows and columns 1 through 10, and this is the way. So 0 if they don't have an edge between them, and 1 if they have an edge between them. So you need to type all the matrix like this and make sure the last line stops here. Okay, so the last line stops here. It's not, the cursor should not go to the blank line, so it should be right here. Alright, so this is how you come up with a matrix, and you can load that to the adjacency matrix based eigenvector program. This should be loadable, so let me save this. I'm not sure it's the same graph. It might be the same graph. I'm not sure. So let us copy this guy there. You can load it from anywhere, but just let me copy it here. so let me now unzip this folder. So press Control C to copy the files and just copy that folder here as I'm doing. That should be good enough to unzip the file. Okay. So now go to the folder and double click on the executable jar file for adjacency matrix EDC. And now load that matrix text file. You're still saying that's a text file. Alright, so it's the same matrix, representing the same graph. So you get the same numbers. Of course, it's printing, the output is from the lowest, the eigenvectors are printed from the lowest eigenvalue to the largest eigenvalue. That's how, it's a long time I did it. Okay, so, but the numbers should still be the same. Okay, so this is the largest eigenvalue and the corresponding eigenvector. Alright, so you can use both, either one of them, to get your eigenvalues and eigenvectors. Alright, so let us look at this property. So if the matrix is going to have all positive entries, like adjacency matrix always has 0 or 1, right? So it's all positive entries. Then the principal eigenvalue is going to be always positive, and the entries in the principal eigenvector are also going to be always positive. So this is a property from math literature, that if the matrix that you are using as a basis to compute the eigenvalues and eigenvectors have only all positive entries, means either 0 or all positive values, then the principal eigenvalue is guaranteed to be positive, and all the entries in the principal eigenvector are also guaranteed to be positive. Why is that? Because if the matrix has some negative entries, the principal eigenvalue could be negative, and the entries in the principal eigenvector could also be negative. And even for adjacency matrices in which this all entries are either 0 or 1, you could still get some negative eigenvalues, but the principal eigenvalue is going to be guaranteed to be always positive. So you get some negative eigenvalues, and also the entries in the other eigenvectors could be negative. As you can see, for 1.888, some entries in the eigenvector are negative. So you could have negative entries in the eigenvector, and actually you need to have some negative entries to satisfy one interesting property also among the eigenvectors. So let me make sure you have time. Okay, so one property involving the eigenvectors is this. So you see, somewhere I would have mentioned that the directions in which you are projecting the graph are mutually perpendicular, and what it means is the eigenvectors, or the projections in the different directions. So you have 10 vertices, you're going to have 10 projections in 10 different directions, and which direction gives you the maximum amount of information about the graph, that's the principal eigenvalue, and that's the corresponding principal eigenvector. So that's why we make use of that most of the time. So that projection gives us the maximum information about the graph. So like, for example, eigenvector centrality corresponding to the principal eigenvector gives us information about, or quantifies, the degree of a node as well as the degrees of its neighbors based on these numbers, right? So that gives us more useful information. Whereas the other directions, the projections in the other directions, don't give us that much useful information. That's why we typically call this as a principal eigenvalue and principal eigenvector. Now, the property I was about to explain is any two eigenvectors, they are mutually perpendicular to each other. That means what is called orthogonal to each other. So in a math class you might have come across this terminology, orthogonal vectors. So that means the vectors are perpendicular to each other. That means what is called the dot product of any two eigenvectors should be 0. So have you all come across what is called a dot product? That's going to be nothing but something like this. Let me use a small example. So let us say 2, 1 is one eigenvector. Let me add one more entry. Say 2, 1, 3 is one eigenvector. And let us say -1. I should have come up with 2, but that's okay. 2, -1, 2. 3, that is 6, negative 6, 2, let's make it 4, this should be fine. So these two vectors, okay, these two vectors are orthogonal. Why? If I take the dot product of these two vectors, so dot product is term-wise multiplication and doing the addition. So 2 times this negative 4 plus 1 times this 2 plus 3 times this 2 is going to be what? Negative 8 plus 2 plus 6, that is 0. So we say the dot product of two vectors, so we can represent it like a dot and then this. So the dot product of these two vectors is, if it is 0, then we say the two eigenvectors or the two vectors are perpendicular to each other or orthogonal to each other. So that's what we are going to observe. If I take any two eigenvectors I have listed here, so let us pick the first two. So 0.4741 times its corresponding entry in the other vector, 0.0641, right? So if you do the math like this, 0.4741 times 0.0641 plus the next entry, 0.4568 times 0.2043 plus, and do all the pairwise multiplication. The last one is 0.881 times negative 0.339. So all the 10 pairs you multiply like that, okay, and do the addition, the result will be 0. You don't need to cross check. Okay, if you do it by yourself you can cross check, but the application, the program is going to do it the right way and give you the answer. So the dot product of any two eigenvectors is going to be 0. So that indicates that the eigenvectors are mutually perpendicular to each other. Okay. And not only that, they are already considered to be what's called normalized in a scale of 0 to 1. So the eigenvectors, I'm looking at the principal eigenvector. So the principal eigenvector, the value is always going to be between 0 to 1. In any other eigenvector, the values are going to range from negative 1 to positive 1, because we can have negative values. So in the other eigenvectors, the values are going to be from negative 1 to 1. Whereas in the principal eigenvector, because we are using the adjacency matrix that has all zeros or all positive entries, the values are going to be in the range 0 to 1. Okay. Alright, so with this, let me see what time is it. Okay, so let us stop right now. So we'll start with this spectral radius topic next time and see some applications of eigenvalues and eigenvectors. So what I encourage is, in the next 1 week before we meet, I would like each of you to download the zip file I have posted in Canvas, unzip it, and try this graph or any graph you might want to try with, and try to get the eigenvalues and eigenvectors and take the dot product if you want to, and analyze all the stuff. And also you can go through the rest of the slide if you want to have an understanding of what we are going to discuss. Okay. So as I do this, you can also practice this if you are having computer on your side, okay, or you can practice after the lecture. But it's all like running the program, getting the values and using those results to analyze something. Okay, so you need to store the results somewhere or keep it open like this all the time and do the analysis, whatever the way you want to do it. Okay, so we'll stop the video. If you have any questions, you can